Hey everybody, welcome back to Young Engineers of Today. I hope you had a good weekend, and I hope you're ready to continue with model rocketry. Anybody do anything interesting over the weekend? All right, well, I'll take that as a no. I guess that's, you gotta have quiet weekends every once in a while too. That's always nice. But yeah, um, we're going to continue with model rocketry. This time we're going to talk about motors that you would put into the rockets. We're also going to spend some time reviewing the fins and stuff like that as well, just so that'll be fresh in your minds again. Just because that was a fair amount of information in a fairly short period of time, and it was last week, so, couldn't hurt. Anyway, last Wednesday we talked about fins. We talked about how they're the main stabilizer on a rocket. Duh. But how they're structured can affect how the rocket flies, so we wanted to make sure that we went over basically why you might want to structure them specific ways. The reason why we want to keep track of that is because fins have to worry about drag. Just like pretty much everything else on a rocket that is directly facing towards the direction that it's moving. But fins, especially because they stick out and they're, they're additional sort of force on top of just the rocket shape itself. Drag is something that exists as long as, you have something accelerating within an atmosphere or moving within an atmosphere. So it's something that's just sort of an ever-present problem for engineers and stuff like that. Hey, Cohen. So for that reason, you kind of want to take a look at everything and see how fins can affect it. One moment. Sorry, my headset was tangled up like crazy and a bunch of other cables that I had on the desk, and was basically pulling me, so I was sitting hunched over at my desk, trying to make my life a little bit more comfortable. Anyway, so drag is something that you have to worry about. You've got induced drag and profile drag. Induced drag is basically drag that only exists whenever the fins are correcting the rocket's flight path. That is to say, the rocket tries to turn, and the fins will actually work against the air of the rocket, or excuse me, they'll work against the change in airflow to keep the rocket pointed in the same direction. Most model rockets don't really have, certainly like smaller model rockets and stuff like that, don't really have this issue. They're very good at continuing to fly straight up. So induced drag, it tends to be pretty low. Profile drag, however, it comes from the shape of the fin itself and is always present under velocity in an atmosphere, no matter what. Think of a boxy car versus a sleek car. So, profile drag is something that just always exists. And so for that reason, you have to think about how your fins are going to be structured and stuff like that. However, we talked about Reynolds numbers, which were basically just numbers that represented how smooth or turbulent an airflow is. And remember that air is a fluid as well, because fluids just represent things that move fluidly. So gases and liquids are fluids, but solids are not. So yeah, a Reynolds number basically describes whether a fluid is very smooth in its movement or laminate, or very bumpy and chaotic or turbulent. The higher the Reynolds number, the smoother the airflow. So we want higher Reynolds numbers for very smooth and orderly airflow. We want that, but it's not always going to work out that way. Then we looked at how a Reynolds number was calculated, and it has to do with the density of the fluid versus how fast it's moving, and the viscosity of the fluid and things like that. And we can use it to not only predict the turbulence of a fluid, but also where that turbulence begins. The reason why that's important is because fins, just by their very design and nature, do better with higher Reynolds numbers. they have more control in areas with higher Reynolds numbers. And because of how rockets are structured and because, physics are a thing, Reynolds numbers tend to be pretty low near the body of the rocket because the nose cone is pushing air out of the way, which creates turbulence. So as you can see, this little diagram right here, you got those crazy red lines right next to the rocket body and then the smooth red lines further out. So you always want to, sort of make sure that the fins are at least able to reach some area of laminar airflow, which means that you're going to have longer fins. Because if the fins are very short, they're not going to do a very good job at reaching that laminate airflow and thus not do a very good job at keeping the rocket steady. However, the larger the fins, the more profile drag you're going to have. So, you kind of run into the situation where you have to have fins that are large enough but also don't have crazy, crazy profile drag. So enter fin shape. Fin shape is also something that is important in fin design, obviously, because fin shape will affect how well your rocket flies. And we spent a little bit of time talking about that, different fin shapes and stuff. And one of the things I mentioned last time was that something like a rectangular or a parallelogram style fin shape would probably do better in keeping the rocket steady and also, be just overall a better design. The reason for that is because while this general design it does better with words, with profile drag, it actually performs fairly poorly at low Reynolds numbers. So you are forced to make the fin larger in order to be able to reach those areas of higher Reynolds numbers. In addition, let's say, the edge of the fin is at a higher Reynolds number. Well, that means that roughly this area right here is going to be hitting laminate airflow and controlling the rocket to the best of its ability, which is certainly less than the area over here. Now, the reason why I filled that in is because I want to show you guys, for comparison, that one. See how much surface area, how much more surface area this rectangular fin is providing? Now, on top of that, rectangular fins, parallelogram fins, they tend to do better at lower Reynolds numbers anyway. So for that reason, you can even make them a little bit smaller, which would reduce their profile drag. The design overall is going to probably have higher profile drag just because it's so dang big, but the higher profile drag is offset by its greater control, its greater amount of induced drag at the right moment. So for that reason, having a rectangular fin probably, maybe, could be potentially, possibly, your best option. Certainly insofar as these different designs are concerned. Erase that drawing. But anyway, that was fins. That's what we spent last Wednesday talking about. All in all, not, too bad. It was just a decent amount of information. So now let's talk about motors. Now, either you'll find this more exciting or you'll find it less exciting because there's also going to be a little bit of math involved in here as well. I'm not going to go into, gigantic detail about it just because there are a number of things to cover, and this is not really meant to go into the nitty-gritty of how all that stuff works. This is meant to be sort of an introduction of design and why you might make certain design choices and things like that. So for that reason, you're not necessarily going to be getting the whole sort of rundown of physics from me. However, it's good to spend some time talking about it, so let's go ahead and do that. So first of all, it's kind of important to understand how exactly motors work from a physics perspective. And you may already know. You may not, but you probably have a decent idea. I mean, we all know that a motor spits out stuff, and it burns because the fuel is ignited and blah, 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 blah. But how exactly does that make something move? Well, Newton's third law states that for every action, there is an equal and opposite reaction. And this is just an observation on how the world works, the universe works in a physics sense. So for every action, there is an equal and opposite reaction. For every exertion of force, there is an equal exertion of force that happens in the opposite direction. So in this picture here, the motor is shooting out thrust from the back. The opposite reaction in this case is the pushing of the motor forwards into the little sort of holder they have here. In the case of a rocket, that's the movement of the thrust backwards, the air moving backwards, things like that, which is causing the entire rocket to move forwards. The opposite reaction in this case is the rocket moving forwards. Pretty basic stuff, right? In the example here, this is the explosion forcing the cannonball this way, which is actually forcing the cannon backwards, or vice versa. Really, it depends upon your perspective which one is the initial force. So anyway, the motors apply a downward force, which is the action. Then, in this case, the reaction is the rocket flying upwards. Let's take a look at the math. So this is some math. This is the math that's actually up here. The force of gas is equal to the force of the rocket. That's what the big capital F stands for. It stands for force. And this is, you have Newton to thank for this as well. This is Newton's first law, which is force is equal to mass times acceleration. Wow. Let me try that again. Acceleration. And I'm sure you guys have gone over this in physics class or whatever, but just to be certain, I'll spend some time talking about this. So when we're working in physical sciences and things like that, we use metric units. And that's because A, most of the world uses metric, and B, because the metric units, the metric measurement system actually does a very good job at having all of the units sort of be interrelated to one another. So like 1 milliliter is 1 cubic centimeter of fluid, just basically, in some sort of container. 1 degree Celsius is 1/100th of the gradient between the freezing point and the boiling point of water. I believe 1 joule is the amount of energy required to raise 1 milliliter of water 1 degree Celsius. So that is to say 100 joules could either raise 100 milliliters of water 1 degree Celsius, or they could raise 1 milliliter of water from freezing to boiling. Stuff like that, like the metric system units are all very intertwined. So it's for that reason as well that we use them in a lot of our equations, because then the math works out nicely, and we can relate them to units that make sense to us and things like that. So let's take a look at this equation fast. Force equals mass times acceleration. Mass in this case is measured in kilograms. Acceleration is measured in meters per second squared, because it's acceleration. Meters per second squared is the same thing as meters per second per second. Meters per second is simply speed. We're generally very familiar with speed expressed in miles per hour, which can also be shown as miles per hour. So meters per second is simply a unit of speed. This is how quickly your speed is changing, how quickly your measurement of meters per second is changing in a given second. That's what meters per second squared is. That's what acceleration is. I mean, you guys were probably able to, glean that from the fact that I called it acceleration. When you think of acceleration, you think of a car moving from a stop to a given speed. That is exactly what's going on here. Now, it's also important to note that deceleration is a form of acceleration as well. It's just acceleration in the opposite direction. You see this more often in, you see it more often with rocketry and stuff like that, because a lot of times a rocket has to flip around and do a burn in the opposite direction in order to bleed off velocity and stuff like that. Deceleration can more be thought of a removal of magnitude from a vector, whereas in a rocketry sense, slowing down is more accelerating in a vector in the opposite direction. It's just weird, but don't worry about that too much. Anyway, kilograms times meters per second squared. Now force is expressed in newtons, sort of as an homage to the guy who gave us this equation. And newtons are kilogram meters per second squared. You might be going, what? What a strange set of units. Well, let's multiply these two together. Kilograms times meters per second squared is equal to kilograms divided by second squared times meters. The second squared goes underneath the whole thing because everything becomes divided by second squared, which is that. That's all it is. So force is a measure of how quickly you accelerate something, or how greatly you accelerate something, and how much of it there is. Simply all it is. Now again, this might be review to you or something like that. You might be like, I already knew this. You might not have. So that's why I want to bring it up now. That's all force is it's how much you accelerate a given amount of stuff. Now I've been using mass, and I've been very careful to use the word mass. I haven't used the word weight at all. And a lot of times when you guys are, talking about mass and weight and stuff like that, and just sort of in an everyday conversation, they tend to be interchangeable. And that's the thing, because we use weight as a way of measuring mass. But here's the thing, that's not a complete picture. In fact, that gives us additional information. You see, for instance, let's say you're standing here on Earth, your weight's a certain amount, right? And you're standing on the moon, your weight's a different amount. You're standing on Mars, your weight is a third amount between the moon and the Earth. So you've got 3 different weights there. However, you have not changed insofar as mass is concerned. You are still, presumably, made out of the same number of atoms that makes up you. You have the same number of atoms that comprise your body. You haven't gotten any like taller or shorter or, whatever. So the weight has changed, but the mass has not. Now here's the deal. Weight is equal to mass times gravity. Nice. I'm glad you love it. So weight is equal to mass times gravity. Now gravity is, on Earth at least, 9.8 meters per second squared towards the Earth. It's always going to be towards the Earth. We don't go 9.8 meters per second squared upwards in the air or something like that. We go towards the Earth. 9.8 meters per second squared, though, hey, what does that look like? Well, that looks kind of like that. And this here looks like this here. So what's gravity? Gravity is just an acceleration. That's all it is. So what's weight then? Weight is just a force. Weight is a force. You step on a scale, you're measuring force. From that, we can glean exactly how much mass you have because we know the acceleration of Earth's gravity. But When you're measuring weight, you're measuring force. So that's why I've been very careful to use the term mass as opposed to weight, because those two are not the same thing, despite the fact that they tend to be in sort of popular nomenclature. And on top of that, we can divine mass from weights. So that's just a little aside. That's not really that necessary to know, but later on it becomes necessary to know. If you go further into physics, it becomes necessary to know. If you start doing stuff like this, it becomes necessary to know. It becomes necessary to make the distinction between the two. So for that reason, I wanted to bring it up now. But anyway, the other confusing thing is when we measure weight, we use units of mass. We don't say, oh, you weigh 15 newtons or something like that. We don't do that because it's assumed that sort of the question of gravity is kind of brought out of the equation, whatever. Anyway, so let's see here. Where was I? Right, force, mass times acceleration. So we got the force of the gas is equal to the force of the rocket. Why do we have that equal sign there? Well, equal and opposite reaction, right? So even though the rocket is heading in the opposite direction from the thrust of the motor, that's just the opposite part. The equal sign is because it's the equals part. There is the same amount of force being exerted on the rocket in the other direction. It's just in the other direction. So the force of the moving gas behind the rocket is equal to the force that the rocket is feeling in its movement upwards. So we can expand this. So the mass of the gas times the acceleration of the gas is equal to the mass of the rocket times the acceleration of the rocket. The mass of the gas and the acceleration of the gas, we're referring to the gas that is moving backwards behind the rocket, that is being moved backwards. So, air always has a mass. We don't really tend to think about it ever on our day-to-day basis. We tend to think, oh, it's as light as air. But in reality, air is super duper heavy. We have something like 2 tons of air weighing down on us every day. It's just, you've grown up with this. And so have your ancestors, all the way back to, however far back in the evolutionary chain you want to go. Which, yeah, basically everything is equal. Exactly, which kind of makes it, nice and tidy. But we just don't feel that because we've evolved to get used to this kind of pressure. But if we grew up in a vacuum, like if we evolved from some single-celled organism in a vacuum, and we came down here to ground level on Earth, we all get squished. Because air has a weight. And we feel this when we jump into a pool, when we go diving and stuff like that. Because water weighs more. And I'm using weight here intentionally. It has a force on us. There is a force exerted upon us. But I could also say that there is a mass. I know I'm just saying one thing and then saying something totally different the next time around. I apologize. Let me make it clear. Water has a mass. Air has a mass. Water has more mass than we're used to because obviously it's been a while since we've lived in the water, thinking about the tree of life and everything like that. But if you go diving and you dive further down into the water, you can feel that water pressing in on you because you're starting to feel the mass. Yeah, you can die. You can. It's unpleasant to think about, but you totally can. But you can feel the mass, all of that water pressing down on you. So for that reason, we take that into account when we're determining the force. We need to. Otherwise, we can't get a full picture of the force that the gas is exerting. If we don't have the mass of the gas, we can't get the force. Now, the acceleration, obviously, I mean, that one's pretty clear, right? I mean, the air is moving. How fast is it moving faster? Acceleration. So we take the mass of the gas and the acceleration of the gas, we multiply them together, we get the force of the gas, and we know that that's how much force is going to be exerted on the rocket moving upwards. We have the force. If we have the mass of the rocket, we can figure out the acceleration of the rockets. What do I mean? So let's say, theoretically, as a just throwing this out there, these numbers don't necessarily mean anything, but as an example, you have enough um, enough air, and it's moving fast enough, it's accelerating fast enough to give you 150 newtons of force. So that is the force of the air moving from the back of the rocket. So this means that the mass of the rocket times the acceleration of the rocket must equal 150 newtons. Must. Because otherwise, physics isn't working. So since force is mass times acceleration, that means we have to take both into account. So we might know, just from weighing a rocket or something like that, we might know that the rocket's mass is 2 kilograms. Well, 150 newtons divided by 2 kilograms, because using math magic, if force is equal to mass times acceleration, then acceleration is equal to force divided by mass, right? You know, pretty basic algebra stuff. So we divide the force by the mass of the rocket, and that gives us an answer in meters per second squared, the acceleration of the rocket specifically. So if we have 150 newtons and our rocket is 2 kilograms, we know our rocket is accelerating at a rate of 75 meters per second squared. It's going really, really fast. That's 167 miles per hour per second. So it's going 167 miles per hour after the first second. And then it's going 334 miles per hour the second. And then it's going, even faster the third second. That's really, really fast. Again, since it's acceleration, that means that's how much faster it's going a second. So this is linear, and it's related. So that means that the rocket, as the rocket is heavier or lighter, it is going proportionately slower or faster. It is accelerating proportionately slower or faster. So if the rocket is 5 kilograms, that is to say 2.5 times more massive, it is accelerating at a rate of 30 meters per second squared. That is to say, it is accelerating 2.5 times more slowly. At 10 kilograms, which is double the mass of 5 kilograms, obviously, it's accelerating at a rate of 15 meters per second squared, which is half the acceleration rate of 5 kilograms. It's a perfect proportion. And doing this kind of stuff, if we can glean how quickly the air is moving from behind a motor, and how fast that air is accelerating, as well as how much air is being moved, because we've using the power of math and stuff like that, we've already figured out as humans how much the air tends to weigh. But if we can figure out those two bits of information, we can figure out the exact amount of force that engine, that motor, is exerting, or it will exert upon a rocket. And if we know how much our rocket is going to weigh, well, then we can figure out exactly how much our rocket is going to accelerate. Kind of neat, right? So the other thing to keep in mind is that the mass of the rocket includes the mass of the motor used to make it go up, so just slapping a bigger motor into the rocket isn't always the best solution. If you wanted to go a certain speed, it certainly is not always the best solution. In fact, if you wanted to go a certain speed, it's probably one of the least good solutions, depending upon a number of different factors, but that should not be the first place you look if you want to make your rocket go faster, necessarily. You might want to look at stripping down the weight of your rocket in other areas first. This is a problem that aerospace engineers have to think about too. Just adding more fuel to a rocket can sometimes make a problem worse. And we talked about this not Wednesday, but Monday. We talked about that a little bit, talking about how, adding more fuel can sometimes create this situation in which it makes the rocket too heavy to be able to, really be efficient with the fuel, but then you need to have the more fuel so that it can, whatever. A lot of times your solution in that case is to be more efficient about how you use the fuel. But again, ironically, the fuel, having more of it can make it less efficient. Well, it's not even necessarily irony, but whatever. Having more fuel can make it less efficient, which means that, anyway, you're sort of fighting against yourself. But sometimes you really do need a bigger motor, and so for that reason, they come in many different classes and sizes. And there are classifications for these things. So how do we read these classifications? Most classification designations, whatever, come in 3 parts, which give you just about all the information you need to know about it, like in this example over here on the right. This is a motor with designation C6-3, and you just say, C63 or whatever. Or maybe, depending upon who you're talking to, the letter is assumed, and you say, like, oh, what about the 6-3 or the 10-9, or the 10-9 would be kind of ridiculous, 10-5, or the 4-1, whatever. So the first part, which is the letter, denotes the total impulse of a motor. We'll spend a little bit of time talking about impulse later on. But the total impulse is the overall power of an engine, in essence. Letters can range from A, B, and C, and so on and so forth, all the way up to O, which is crazy, because here's the thing. Each letter grade represents double the overall power. So an A-class motor is a certain amount of power. A B-class motor is twice that power. A C-class motor is twice a B. A D is twice a C. E is twice a D, so on and so forth. So at O-class, you're talking really super powerful motors. In fact, everything H-class and above is referred to as high-power model rocketry. So if H is the beginning of high-power model rocketry, and let's see here, A, B, C, D, E, F, G, H, and I'm counting on my fingers. You can all judge me. An H-class motor is 256 times more powerful than an A-class motor. An O-class motor is 128 times more powerful than an H-class motor. That is to say, an H-class motor is the same amount of power as 256 A-class motors, all running at the exact same time. And an O-class motor is as powerful as 128 H-class motors, all running at the same time. Yeah, it's a lot of power. In fact, let's see here, 128 times 256. I don't even want to do that math right now. That's some number around 4,000, I want to say. It's a lot more powerful. Nice. Nice, Cohen. So yeah, the reason why it's referred to as high-powered model rocketry is because there is a whole number of hoops that you have to jump through. And this, by the way, this is a model rocket. I don't know what size this motor is, but I'm guessing somewhere in the vicinity of O-class. But here's the deal. The reason why they have a whole classification for high-power model rocketry is because there needs to be a designation for the government. The reason why there needs to be a designation for the government is because you need permission from the FAA to launch anything that is considered a high-powered model rocket. So just think about that for a second. You need permission from the government to launch these rockets, just to make sure that A, they aren't hitting anything flying in the sky, and B, they could potentially be large enough, leave a large enough signature, and fly high enough that they get picked up on local radar. If the FAA doesn't know it's there, suddenly you've got an unknown flying object, an unidentified flying object, a literal UFO in the air being picked up by radar. And that makes people freak out. That makes people really unhappy. That, depending upon the size and how high it goes, can make the local air defense really unhappy. So you need to you can make the national air defense very unhappy. You need to let the FAA know if you're launching something that size, basically. So anyway, the letter denotes how big, in essence, how powerful, in essence, the engine is. The number directly after the letter represents the average thrust, or how much power it puts out at any given moment versus how long it puts out power. So we've got I guess, in essence, our gas tank, which is the letter? That's an excellent question. I know you guys should probably be building model rockets at some point during lab, but I don't know exactly what the lineup for that is going to look like. In the past, he said you guys build model rockets and launch them off and stuff. Granted, they're not going to be like, crazy engines or anything like that. We're talking probably A or B class, but still, kind of neato. Anyway, think of the letter kind of like your gas tank. In essence, it represents how much you can accelerate a mass over its entire lifespan, that is from full to empty. That's kind of like what the letter denotes. However, let's say you have a car with a full tank of gas. You could drive that car 25 miles an hour, never, or you could be accelerating at a rate of 1 mile an hour per hour. And of course, assuming, an ideal situation, you'd be using very little fuel. You would be basically that fuel tank would last you a very, very long time. You could be accelerating at a rate of 20 miles an hour a second. It's a very powerful car, but you could be. And let's assume that there's no limit to how fast you can make that car go. You could, after 10 seconds, be going 200 miles an hour. You could, after 20 seconds, be going 400 miles an hour. But that gas tank is not going to last you very, very long at all. It's going to, in fact, be a very short-lived gas tank. You're just going to burn through that fuel roughly at a rate of about 20 times the amount that you were in the initial example. Well, that's kind of like what the average thrust number is. So in this case, it's the 10 in A10, it's the 6 in B6, it's the 12 in D12. The higher the number is, the more thrust it puts out at any given moment, however the shorter the burn time is. Because obviously it's burning through its fuel more quickly. So, you could have, in essence, like for instance, a B12 could burn, let's see here, a D12 could burn as long as a C6. The D12 is going to be putting out a lot more power though, because it's got double the amount of average power, but by virtue of its letter alone, and then the fact that it's a higher number means it's going to be putting out a higher thrust as well. But assuming all things equal, yeah, a D12 will run roughly the same amount of time that a C6 would run. It's just the C6 has half as much fuel, but it's burning its fuel half as quickly as the D12 is. D12 has twice as much fuel, but it's burning its fuel twice as quickly as the C6 is. Therefore, they'd be running about the same amount of time. It's just the D12 would just be a whole lot of acceleration compared to the C6. The C6 would be about a quarter of the acceleration. Anyway, the higher the number, the more thrust it puts out, and the shorter the burn time. If you decide to continue with model rocketry, which I get the feeling that at least a couple of you here probably want to, you can always get proficient with using multiple stages for your rocket. Thank you, Kerbal Space Program, for this example of sort of what you could do over here. You could use like a high average impulse to get your rocket off the ground and moving fast. So in that example, you could have like a D12 that's used to just like get it moving up off the ground, like super fast. But it's got enough thrust, it's got enough force to be able to overcome the mass of the rocket. Then you could use a lower impulse set of engines, like you could use a D6, or you could use, I don't know, a number of C6 rockets or something like that, or C, 3 rockets or whatever. You could use those lower impulse engines once your D12 in this theoretical example burns out to keep it moving upwards for a longer period of time. So it could get it off the ground, and then you could have enough motors on there to just basically keep overcoming the effects of gravity. You've already done all the hard work, which is to just fight against gravity and make it go super fast, and then you could have something that's just meant to maintain it and not exactly accelerate it upwards any further. And so you could do stuff like that to get your rocket even further up off the ground. So that's that second number, or that first number. Now the second number, which is the number after the dash, represents how long a delay there is before the ejection charge blows. Now the nice thing is this is very straightforward because, if you remember the delay charge, that third number just tells you how long the delay charge will spend burning in seconds. Now granted, there's always like imperfections in manufacturing and stuff like that, which means that like a B64 won't necessarily burn for exactly 4 seconds on the dot before the ejection charge blows. But that's meant to give you an idea of how long it should. On average, it will be 4 seconds. A D12-5, on average, the delay charge will burn for 5 seconds before the ejection charge goes off. So that's how long your rocket will spend coasting upwards in the air before the ejection charge gets blown and the recovery stage begins to do its thing. So with these three things, you can kind of get an idea of how big a motor you might want for your rocket. But I've been using the term impulse. What exactly does that mean? Well, without getting really into the calculus of it, because impulse is essentially an integral. Excuse me. In essence, impulse is the amount of force over time. It's the average of the amount of force over time, which is different from the average thrust or the average impulse. Because, well, let's see here. Okay. Without getting too crazy in depth, if you've ever taken calculus before, oops, you know that calculus is the math of change. Calculus is meant to give you an idea of how much something changes over time. Calculus allows you to take an equation like speed and derive it to get acceleration. You can even derive acceleration to get an idea of how much acceleration might change over time, which is called the jerk. I'm not kidding. Because you think about like the very beginning of an acceleration. Like if you have your hand on something and you move your hand away very quickly, think about that first moment when your muscles are all engaging to pull your hand away from where it was. The beginning of that acceleration, you can think of like, oh, you jerked your hand away really quickly. Well, any particular moment in that acceleration away is referred to as a jerk. Yeah, wow, what a jerk. So then you've got acceleration, and you got speed. But the thing is, whereas calculus allows you to figure out these equations, it also allows you to figure out equations in the other direction. Yeah, exactly. Assuming some additional information as well, but you can use then the speed equation in order to figure out position. Oh, gotcha. Nice. So you can sort of work upwards on the chain as well. If you have acceleration, you can figure out an equation for the speed. You can figure out an equation for their position from there. So you can have an equation that's just a position. You can say like, okay, given the starting position and given a certain amount of time, where will IB after so many seconds or whatever. So you can do that as well with calculus. In our sort of continuation here, we've got our force. Let's just do this. We can move one up and get the impulse. That way we can get an idea of how much how much force is being exerted at any given moment, but just sort of an average of it over time. So it's not quite force because it's just speed as opposed to acceleration. It's sort of strange to explain, but basically impulse is an overall look at the amount of force that's exerted over time, over a specific amount of time. So when we're talking about total impulse, total amount of thrust that's exerted on something, total amount of force that's exerted on something over its entire lifetime. Average thrust is how much thrust, or average impulse is how much force it's exerting at any given moment of time, without taking into account how long it lasts necessarily. I mean, the two are assumed because average impulse is total impulse just divided by time, in essence. But anyway, you want to basically sort of use these concepts in order to get a better idea of how your rocket would perform, but you would need to know like how much your rocket would weigh versus how fast you might want it to go, and then you can sort of use that information to divine a good class and average impulse of engine and stuff like that. And then if you knew, like how fast it was going at the end of the propellants, you could then figure out how long you'd want the delay charge to be, so that it's going basically either as slow as possible before the ejection or before the recovery blows, or whatever. And so, given those three things, you could figure out what kind of engine you'd want to put in your rocket. D12. There you go. Anyway, that's going to do it for today. That's actually everything I got on model rocket engines, model rocket motors. It's true, go big or go home. So with that, I'm going to go ahead and end this lesson here. We'll spend Wednesday talking about recovery systems and maybe some other stuff too. I mean, because recovery systems is not one of those decisions that you need to agonize over as much. Those tend to be pretty clear-cut, for the most part, sort of. Certainly more so than fins and stuff like that. But, spend some time talking about that. And then next week we're going to continue more with the stuff. And at some point within the coming weeks here, we're going to start using OpenRocket, which is a simulation software, which should be pretty cool, which will allow you to sort of model this kind of stuff out and get all kinds of graphs and things like that to figure out how it's going to perform. These graphs are always awesome. Anyway, so let's go ahead and do the poll questions now, and then we'll go ahead and leave it open for question and answer time. If you don't have any questions of your own, once I've asked the poll questions, you're more than welcome to head out. Have a wonderful couple of days, and we'll see you on Wednesday.